In this video, we're going to look at the power series. The power series is a series of the form. It's a summation of a coefficient of the nth term and then times x to the n. So x is a variable in this situation. It is not the n, and that's going to stay the same throughout the whole problem. For each fixed x, the series is a set of constants that we can test for. So we're going to be looking for which values of x allow me to do convergence and divergence in the problem. So it may converge for some values of x and will diverge for some other values of x. So if we look at it's the sum of those values. However, if I take the cn away and I just make it 1, I actually have a geometric series. And in this geometric series, I know, just like in the geometric series we looked at before, that they're going to converge when x is between -1 and 1, and they're going to diverge if the absolute value of x is greater than or equal to 1. So, for example, if we put in 1/2, I get the geometric series of 1 plus 1/2 plus 1/4, and we know that one converges. And if we plug in 2 for the x, that one would diverge. So that's just a little bit of a way what the power series is. We're going to start looking at some examples of those in the next coming slides. Here we have the more general series of the power series. It's a summation of c to the n, and it's x minus a to the n power. What this allows us to do is it now allows me to shift the power series. So it's known as the power series of x minus a, or the power series centered at a. When we're looking at this, though, we have the n to the 0 term, and that's very important because x minus a to the 0 power is 1, so I don't have to worry about that no matter what a is going to be. In this example, we're going to look at the series n factorial times x to the nth power. I'm going to see where it's convergent. So for this one, because it's a factorial, I'm going to use the ratio test. That's the easiest way to go about doing this one. And we're going to let a to the n donate the nth term of the series. Now, we have to take the assumption that x does not equal 0 in this situation. Because if x equals 0, then the denominator of my ratio would be 0, and we can't have that. So we're going to make the assumption that x does not equal 0. Now we plug it in. We have n plus 1 factorial times x to the n plus 1 over n factorial times x to the n. When we simplify that one down, the n factorial will cancel out, and the x to the n will cancel out, and I'm left with n plus 1 times the absolute value of x. Now, as that limit goes to, as n goes to infinity, that's going to go to infinity. So based on the ratio test, this series diverges when x does not equal 0. So the only time the series converges is when x equals 0, because it actually converges to 0. So that's how we would actually do this problem. That's a general sense of what the power series is we're going to be looking for the x values on when it's going to diverge and when it converges. So we're going to have those two options instead of just always converging or always diverging. In this example, we're looking at the series x minus 3 to the nth power over n, and we want to know when it converges. So again, we do the ratio test. X minus 3 to the n plus 1 over x plus 1 divided by, or times, in this case, n divided by x minus 3 to the nth power. Simplify that down, we end up getting n over to the n plus 1 times the absolute value of x minus 3. Don't lose the absolute value, because in this case, unlike in a lot of situations that we looked at, the x minus 3 can be negative, so that absolute value is very important. Doing the limit to this, we have 1 over 1 plus 1 over n, so that goes to 1. So this basically goes down to the absolute value of x minus 3. We now have to look and set up with the ratio test, and we know that the ratio test converges when it's less than 1 and diverges when it's greater than 1. So I have the absolute value of x minus 3 is less than 1, which means it's -1 is less than x minus 3 is less than 1. So it's going to converge from its 2 is less than x is less than 4. And we know it's going to diverge when x is less than 2 or x is greater than 4. We don't know what's happening at 2 and 4 yet, so we have to actually do those two tests as well. So we're going to look at those individually. If we plug in 2, I have 2 minus 3, which is going to be negative 1. So I get negative 1 to the nth power over n, which, if we remember, is the alternating harmonic series, which converges. When I plug in 4, I get 1 to the nth over n, and that is the harmonic series, which we know diverges. So when we put all this together, the series converges when 2 is less than or equal to x and less than 4. And that, notice how the equals is on the 2 because we know it converges at that point. And it diverges when x is less than 2 or when x is greater than or equal to 4. So in a power series, we have 3 distinct possibilities. The first one is the series converges only when x equals a, which means that that's going to be the 0. The series converges for all values of x, which means it would go from negative infinity to infinity, any value of x. And that there's a positive number r such that the series converges. R is known as the radius of convergence, and this is very similar to the example we just did in problem number 2. So one case, we have single point, or negative infinity to infinity, or we have a range of values. When we look at this, the geometric series has an interval convergence from negative 1 to 1, so its radius of convergence is 1. The first example that we did, when the value only worked when it was 0, has a radius of convergence of 0, because there's only one value that would work. In example 2 we looked at, we had the interval of convergence was from 2 to 4. So the radius, the diameter is 2, so the radius is 1 in that situation. And then the basal function, which you can look at in your book, which is example number 3, actually has all values will work. So my radius of convergence is infinity, and my interval of convergence is from negative infinity to infinity. We're going to look at one more example of this, and we're going to figure out the interval of convergence and the radius of convergence. So in this example, we're looking for the radius of convergence and the interval of convergence of the series below. As you can see, I'm going to use the ratio test for this, and I've set it up and broken it down. Because if you go through all the steps, we end up getting down to 3 times the absolute value of x is where this would converge after doing the limit. Now the ratio test converges when x is less than 1. So in this case, it is going to be between negative 1/3 and positive 1/3 after solving the absolute value for x to be convergent. Once we've got that, we got to test it at those endpoints. We've got to test it at the negative 1/3 and the 1/3. When I plug negative 1/3 into it, I get 1 over the square root of n plus 1. Now this is going to diverge based on the p series because p is 1/2. Now if I look at plugging in 1/3, this one is going to converge based on the alternating series test. Remember, the alternating series test states 2 pieces. It has to be decreasing and the limit has to go to 0. This one is obviously decreasing and the limit is actually 0 as well, so therefore it converges there. So the series converges between negative 1/3 and 1/3 inclusive. And the radius of convergence is 1/3 for this problem.